Hello everyone, I am Aljaber Mahmoud from Department of Electrical and Electronic Engineering of Islamic University of Technology, Bangladesh. Today I am very excited to share our recent work, which is Firefly algorithm-based optimized PID controller for stability analysis of DC to DC SEPIC converter. The paper ID is 1570773442. This paper contains an abstract, introduction, some literature reviews, objectives, the state space average method, implementation of optimization algorithm in PID controller, and results and conclusion. The goal of this research is to examine the stability and enhance the performance of closed-loop SEPIC converter by using the Firefly algorithm technique in the construction of an improved PID controller. Observing the performance parameters, which is percentage of overshoot, rise time, settling time, and peak amplitude, comparing the result based on the four objective functions, which are IAE, ISC, ITAC, and ITAE. In power electronics, DC to DC converters are essential in improving the energy conversion efficiency. A higher order DC to DC SEPIC is observed containing 4 poles and 3 zeros. Modeling of SEPIC is done by the steady space average method. In the steady space averaging method, the switch circuit is divided into 2 or 3 different structures. The derivatives of inductor, conductors, and capacitor voltages are defined based on circuit theory for every substructure. These current voltages are averaged over the switching device. For switching devices, we use MOSFETs because it provides higher efficiency and higher switching speed. It can operate at lower power and draws no current. Because of the MOSFET, a linear characteristic, nonlinear characteristics also observed that provides a high percentage overshoot and higher output ripple voltage in the open loop system. To control this, the overshoot and ripple voltage, a PID controller is combined with the converter to control its output voltage with step responses and related performance parameters. In case of tuning a PID controller, to get the gain values, we use trial and error method in MATLAB PID tuner. However, this does not give an optimized result for controlling the performance parameters of SEPIC. So for a well-optimized result, Firefly algorithm is used in the optimization process of the controller, which can deal with nonlinearity in the control system. Our work employs the Firefly algorithm to establish a comparative analysis among their respective performance as an optimization process for the SEPIC. This algorithm searches for the local minimum within a search space, and it provides a converse result based on the result. The gain values of the controllers are considered. In literature review, we found some related works. Nishat et al. Implemented SA in PID to analyze the stability of SEPIC converter. Liping Chen et al. Applied the UPSO method in the DFO PID controller for the performance analysis of the SEPIC converter. Amin Al-Qada et al. Utilized the SA optimization technique in PID controller for adaptive regulation of buck and boost converters. Haji et al. Implemented AVC, PSO, FA, and DFA for FOPID controller into chopper converter to gain control over DC motor drive. Yakub et al. Applied FA and GA in the PID controller to analyze the step responses of the optimized DC to DC buck converter. We have set some objectives to work towards and determine whether our works are achieving what they set out to do. The main objectives are analyzing the stability of DC to DC SEPIC with the desired output voltage followed by the input voltage. Designing the DC to DC SEPIC with a closed loop system with a PID controller, observing the optimized PID controller step responses and performance parameters based on the implementation of Firefly algorithm. Here, the circuit diagram of the SEPIC converter consists of 2 inductors, 2 capacitors, a diode, and a MOSFET used as a switch. During on state, the switch is closed and the diode is in reverse bias. The arrow in the figure shows the direction of current. The current through inductor L1 and L2 increases, though current through L2 increases negatively because the capacitor C1 provides energy. During off state, the switch is open and the diode is in forward bias. The arrow in the figure shows the direction of current. The current through capacitor C1 and inductor L2 are the same because switch is turned off. Current through the inductor L2 is negative. For state 1, the equations have been developed based on the current through inductors and voltage across capacitors. Moreover, based on the equations, the matrix form is given to these equations. Again, for state 2, equations have been developed and formed into matrix form. Now let's talk about the Firefly algorithm. Firefly algorithm is a nature-inspired meta-heuristic algorithm created by Jin-She Yang based on the flashing lights of fireflies. Meta-heuristics are higher-level procedures designed to find that may provide a sufficiently good solution, especially with incomplete or imperfect or limited computation capacity. The significance of the fireflies is that all fireflies are unisex, which means one firefly will attract it to another. Attractiveness is proportional to the flashing brightness. As a result, less bright will travel to the closer one. In temperature climates, the flashing light of fireflies possesses 2 primary functions. The flashing light helps fireflies find mates, attract their potential prey, and protect themselves from their predators. FE is possibly more robust in discovering global optimal solution with the least amount of processing time. The new position of the Firefly will be updated based on the shown equation. This here, the second term is because of attractiveness. Randomization is the third term with alpha t denoting the randomization parameter. We have an error function based on the difference between the input and output signals from the closed loop system. 4 fitness functions are used as the objective function, which works based on the error signal to minimize the error. The fitness functions used in our work are IEEE, ISC, ITAE, and ITAC. This slide shows that a closed loop system is system which is based on the optimized PID controller by Firefly algorithm, which is given as a flowchart. MATLAB system identification tools has been used to find the reduced order transfer function and in the results and simulation parts. 4 performance parameters have been analyzed: the percentage overshoot, the rise time, settling time, and peak amplitude. Based on them, a comparative analysis is shown at the end. This is an open loop SEPIC circuit done in the Simulink, where MOSFET is used as a switching device for reducing the switching power loss. These are the values of different parameters of the circuit, where the value of C1 kept higher for having a low ripple voltage across C1. The transfer function and step response for the open loop system is shown here. It can easily be said that the performance of the open loop system is very poor, as all the performance parameters are very high. So to overcome this situation and control the system, is closed loop SEPIC with a PID controller is introduced, designed in the Simulink. By tuning manually in the PID tuner app MATLAB, we found these gain values for PID. Using these gain values, we found the performance parameters through step response of conventional PID controller. The percentage overshoot is 9.52%, rise time is 0.423 seconds, settling time is 3.62 seconds, and peak amplitude is 1.0952. This performs better than the open loop, but not so good as expected. For getting the better performance from the closed loop of SEPIC, the optimization algorithm FE is applied. Using the different objective function in implementing the FE algorithm, we found 4 different proportional, integral, and derivative gain values. Using these values, step responses are generated. The performance can be observed from this table for 4 different objective functions. Step response of IEEE and ISC is shown in this slide. ITAC and ITAE in this one. Merged step responses of conventional and 4 objective functions are shown in this slide, where we can differentiate the different performance parameters in each case. A comparative chart is shown where we can see that the conventional case and the performance parameters are the worst. Nevertheless, by using the Firefly algorithm, we are having better performance. In terms of percentage overshoot, ITAE has 6.11%, which is worse than other objective functions. But IEEE has 2.14%, which is the lowest. In terms of rising time, 0.393 seconds is the lowest value, which is for ITAE. Again, in settling time, the highest is 4.6 seconds for ISC, and the lowest value is 3.08 seconds for IAE. Peak amplitude follows the same pattern as the percentage of overshoot. In conclusion, we can say that the percentage of overshoot, settling time, and peak amplitude, FAPID of IAE has the lowest value, that is 2.14%, 3.08 seconds, and 1.0214 respectively. FAPID of ITAE has the lowest value of 0.393 seconds for rise time, but worse in other cases. In overall performance analysis, it can be observed that FAPID of IAE performs better than others. Furthermore, it is evident that an optimized PID controller performs far better than a conventional PID controller. References used for this paper are given in the following 3 slides. That's all from our side. Thank you everyone for your time.